Hello everyone, I am Jyoti SK, Assistant Professor Department of ECE-Nagarjuna College of Engineering and Technology. Today we will learn how to design a combinational logic circuit which outputs when its input is illegal BCD. So we will be having 6 steps to design the circuit. So let me write the first 6 steps which you have to know before we start with the problem. That is, first step is problem statement. Then we will have a truth table representation. So the fifth step we have here is logic design representation. So once you are done with the Boolean expression simplification, we will design the particular circuit. After that we have the last step, that is logic circuit representation. So firstly, it is necessary for you to understand what is the problem statement in the particular problem given, that is designing a combinational circuit which outputs when its input is illegal BCD. So it is evident inputs in this particular problem is A, B, C, D. It can be any other W, X, Y, Z. You can name it accordingly. So when we say that it is a binary coded decimal, it is very obvious that you will have a input that is from 0 to 9. But since it is a 4 input combination, you will have from 0 to 15. Okay. Next, what is the output will only generate when your input is illegal BCD. Also you can see that the question says logic circuit which outputs. That means you will have only a one output. We will consider it as Y. So very necessary in the problem statement that you need to know the relation between the input and the output. So what is the relation between the input and output here is it will give you an output only when the input is illegal BCD. So you just write here illegal BCD is your problem statement. Whenever in the particular input combination you will get an illegal BCD, only then you will be writing an output for it. So firstly, we are done with our problem statement. Second is a truth table representation. Now we know that what is a truth table representation. We will have, as we have decided, that we will have how many inputs there? 4 inputs, namely A, B, C and D. Output we have with us is Y. Okay. Now we all know that we will go with the 15 combinations, that is from 0 to 15, 8421 code system. The first one will be your 000, next one will be your 001, next is 0010, then we have 0011, 0100 because it's a 4, then we have 0101, 5, 0110, 6, 0111, okay. Then we have to write 8, 100, 1001, that is 8 plus 1 gives you 9. Then we have 10, 1010. We are done with 8 plus 2, 10. You can see that your 1 is in the place of 8, another one is in the place of 2, that is 8 plus 2 gives you 10. Then we have 1011, that is 11. Next we have 12, 13, 14 and the last one is 15, right? So together we have from 0 to 15, 16 possible combination. Now how do you write the input? We have done with the input, how do we write the output is the case. So we know that it will output only when it's illegal BCD. What do you mean by illegal BCD? You know that binary coded decimal is nothing but from 0 to 9. So from 0 to 9, you will write your output as 0. Rest from 11 to 15, you will be writing the output as 1. Why? Because they have said us in the question, design a combinational logic circuit which outputs when its input is illegal BCD. So for all the combination from 0 to 9, you will be writing the output as 0, because from the problem statement we know that binary coded decimal is from 0 to 9. Here this is 8, then we have 8 plus 1, 9. Now rest part is 10, 11, 12, 13, 14 and 15. So all these combinations will have your output as 1. Why? Because from the question we know that we need to know the output only when the input is illegal BCD. So this will be your second part, which is called a truth table representation. Third one, I'll just finish with the third one, then we will continue with the next continuation of this video. So next we will have a Boolean expression representation, which is very easy to write. So you just have to write y is equal to the output. Wherever you have the output as 1, that is 10, 11, 12, 13, 14, 15, you will have to write summation of 10, 11, 12, 13, 14 and 15. So this part we call it as a Boolean expression representation. So basically where your output you have termed it as 1, that is from 10, 11, 12, 13, 14, 15, you will write it in terms of y. That is, we call this summation is nothing but your minterms, or you can call it as a sum of product. If you are deriving it for the product of sum or max term, you have to write this in terms of pi. So now here we will be writing in terms of SOP, that is summation. So summation is nothing but 10, 11, 12, 13, 14 and so we are done with the Boolean expression representation. We got it as y is equal to summation of 10, 11, 12, 13, 14 and 15, right? So next step would be our fourth step, that is Boolean expression simplification, which will be done by a K-map. So we have a K-map here. Why is it a 4 variable K-map? Because it is a 10, 11, 12, 13, 14, 15 means we will have a 4 inputs with us. So we will be drawing a 4 variable K-map, which will have the inputs A, B and C, D. As you know, how do we write? 0, 0, 0, 1, 1, 0, 1, 1. Similarly with the rows and the columns. The place value for the K-map, we know that 0, 1, 2, 3, 4, 5, 6, 7. Then 8, 9, 10, 11 should be in your last row. 10, then 12, 13, 14 and 15. Now, wherever we have a minterms with us, that is 10, 11, 12, 13, 14, 15, you write those minterms as a 1. Why? Because it is a summation or sum of product is termed as 1. The value is output as termed as 1. Whereas if it was pi, that is POS, product of sum or pi notation, then we will write it as zeros. So now coming to the grouping of this particular K-map, we always know that in the K-map, you will always have to aim at the highest grouping. We can see for the grouping of 16, then followed by 8, then followed by 4, then it is 2 or 1. The single grouping is also possible if there is no any groupings left. Now 16 is not possible here, 8 is not possible. Now we have a grouping called 4 here, 1, 1, 1. Then rest 2 these place values of 11 and 10 are vacant. Even here this can be grouped, which can be a group of 4. So now you need to write, you need to simplify this further. You can write this as the value of this particular grouping is nothing but corresponding row to this particular grouping is 1, 1. Corresponding columns are 0, 0, 0, 1, 1, 1 and 1, 0. You can see that this whole thing is covered by all these minterms. Now 1, 1 we have left with, which can be written as A and B. Why are we not writing all this? Because it will get cancelled with all other minterms 0, 1, 0, 1 and 1 and 0, right? Next, which is the second group we have? We have a second group here 1, 1, 1, 1, which is in the place value of 10, 11 and 14 and 15. So for this particular grouping, that is second group, we have the rows in AB inputs 1, 1 and 1, 0. So here 1 and 0 will cancel. We are left out with A, right? In this particular group, again we have 1, 1 and 1, 0. 1 and 0 will cancel out. What remains with us is 1. 1 is nothing but C. So Y is equal to AB plus AC. Therefore, the Boolean expression simplification for this particular sum would be y is equal to AB plus AC. Next, we are done with the Boolean expression simplification. Logic design representation, which is very easy one. You just have to represent your sum. That's it. That is, this one would be of illegal BCD. Design representation is nothing but you just have to write how many inputs you have given. That is A, B, C, D is your input. Output is nothing but Y. So it is very simple. We are done with the logic design representation as well. That is our fifth step. Now coming to the last step, logic circuit representation. So now how do we design a logic circuit? We already have with this the simplification y is equal to AB plus AC. You just draw the inputs like this A, B, C and D, and the negation of those inputs can also be drawn. So when I say negation of these inputs, it is nothing but A bar, C bar, B bar, C bar and D bar, which was actually not necessary for this particular sum. Why? Because we have the output as AB plus AC. So the first one is AB. You just have to take an input from A and the B. So since A into B there is AND, you will write an AND gate. Then AC, again take the input from A and C, AND gate. Now between these two AND gates we have a sum term, that is OR gate. So plus is represented in terms of OR. That will be your Y is equal to AB plus AC. So first one was your AB, which is AB. This is your AC, AC, right? Now these are the 6 steps you need to follow to design a combinational logic circuit. It can be any other problem with any other scenario. Here it was when you have to write your output only when the input is illegal BCD. So we know that binary coded decimal is nothing from 0 to 9. From 10 to 15 you will write your output, that is summation of this one. Followed by the K-map simplification, logic design representation, and last one is logic circuit representation. Thank you everyone.